In this video, we're going to do an example where we find the centroid of a cone. So consider a solid cone with its tip at the origin. It has a height of 1 and base radius equal to 1. And I want to find its centroid. So the height here is going to be 1, and this base radius, which I'm calling A, is going to be 1. Remember that the term centroid means we're trying to find the center of mass. Find the center of mass in the special case when my density function equals a constant, which I'll call K. So my density is constant. So I'm trying to find where that center of mass is. Where is the center of mass of this object going to be? And I first want to have you pause the video just for a quick 30 seconds, because it turns out we can find the x coordinate and the y coordinate of the center of mass just using some logic. So pause it for 30 seconds in 3, 2, 1, pause it, and see if you can figure out what the x and y coordinates are going to be. Okay, so hopefully you did that. Hopefully you paused it to try that. So because the density is constant and this whole shape is symmetric about the z-axis, I would expect the center of mass to be somewhere on the z-axis. Probably closer to the top than it is to the bottom, because there's just more mass on the top than there is on the bottom. So because of that, I expect the x coordinate to be 0 and the y coordinate to be 0. So I'm going to say that this is true by the symmetry of the picture, by the symmetry, and also the fact that density is constant. So those two things tell me this. Like if the density wasn't constant, it might be heavier on one side than it is on the other, and that would pull the center of mass in that heavier side. Okay. So for my z coordinate, we'll use our formula for the center of mass. So I take a triple integral over my region, because my region is 3-dimensional. I need a triple integral. And then you do the z coordinate times the density, but the density here we're saying is k. It's constant. Okay, and then that gets divided by the mass. The mass of the object here is the triple integral of the density, which is just k. Now these constants can get factored out. So they can get factored out, and then once they're factored, I cancel them. So on the top, I just have the triple integral of z, and on the bottom, I just have the triple integral of, technically there's a 1 here in front of the dv. And the triple integral of 1 tells me the size of this shape. And that's because it's 3-dimensional. That means it's the volume. So that's the volume of this shape. And I could just use geometry for the volume of a cone. So that is 1/3 pi r squared times height. And my r is 1, and the height is 1. So multiplying these, we get pi over 3. And that's my volume. That's going to be this denominator. The denominator is pi over 3. So what's left to do is figure out the numerator, that triple integral of z. Okay. So one of the things I'm going to do now is I'm going to convert this whole thing to cylindrical coordinates. In fact, you might be able to tell that just by looking below here in my notes. The reason I'm doing that is this solid, this cone, is circular in nature. In fact, the cross sections are all circles. And we've seen before in our last video that that's a tip-off that cylindrical coordinates is going to be helpful. So when I switch to cylindrical, I got to convert this formula to cylindrical. But in cylindrical, z just stays z. And then I need my Jacobian. Remember, for cylindrical, that Jacobian term is just r. And then I write my dz, my dr, d theta. In cylindrical, we pretty much always do it in this order. So because dz is the innermost thing, I need my limits of integration here in terms of what z equals. So I'm going to draw an arrow parallel to the z-axis through the solid. So an arrow, at some point, it's going to hit the surface of this cone. It'll enter it, it'll go inside, and then it'll exit by hitting the top, and then continuing to go up. So where does it enter and where does it exit? So first off, a little typo. I wrote exists rather than exit. Let's get rid of that s. And then where does it exit? Well, it exits at the surface on top. The surface on top is at the z value 1. So the exiting is when z equals 1. So that goes up top. And then it enters at that cone. What's the equation of a cone? So there's a couple ways to see this. We actually did an example of this in one of our previous videos here, but let's just kind of recap how I could see it if I didn't remember that. Well, if I think about this picture, like if I think about this point at the end, for example, I know if I kind of project that down, the distance from the origin to this spot, that's what we call r. And at least for that one point, r is equal to 1. And this vertical distance, that's representing my z-coordinate. This vertical distance representing the z-coordinate, which is 1, at least at this point. So if I think about the way that r and z are increasing as I go up along the edge of the cone, well, they're always going to stay in this 1-to-1 ratio. So this kind of describes a line with a slope of 1. And that equation would be just z equals r for the equation of that line. Another way I could see that is, if I remember the equation of a cone from before in multivariable, it's z equals square root of x squared plus y squared. And then x squared plus y squared is r squared. And if you square root that, we'll just get r. Okay, so one of those two ways. So, okay, my lower limit of integration where it enters on the cone, that's z equals r. So now to figure out the theta and the r bounds, I have to look at the shadow of this cone on the xy plane. So I'd project this cone down onto the xy plane, drop all these points down, and this circular top will then form the shadow. So the shadow here is going to be the circle. In fact, let me just draw my xy plane and then draw in that shadow. So my xy plane, I will draw in that circular shadow. So that's a circle of radius 1. Okay. And I'll shade in this region. And now to find the limits of integration for r, will I draw an arrow radially outward? And that arrow enters the region right away at the origin when r is 0. So the lower one is r equals 0. And it exits the region on the circle where the equation is r equals 1. And then because I go all the way around my circle, well, theta goes from 0 up until 2 pi. Okay, so I've gone ahead and written out some of the steps already to speed up the process. So I have dz on the inside, so I treat z as the variable, r as a constant. So antiderivative of that would be z squared times r. I got to plug in 1 for z and then r for z. If I plug in 1, I get 1/2 r. If I plug in r, I'll get 1/2 r cubed. Okay, now if I do the antiderivative, I'll get 1/4 r squared minus 1/8 r to the 4th. If I plug in 1, now let's write this out. I'll get 1/4 minus 1/8. And then I got to subtract. If I plug in 0, I'll just get 0. And then I could get a common denominator and subtract these. It becomes 1/8. Then if I do the antiderivative 1/8 with theta as the variable, I get 1/8 times theta. I then plug in the 2 pi and the 0. And if I do that, this just becomes pi/4. So my integral on the top just becomes pi/4. Remember, the one on the bottom represented volume, which we got earlier. The volume was pi/3. And then doing the division, this just becomes 3/4. Okay, so for my centroid, the x and y coordinates are both 0. The z coordinate I now know is 3/4. Okay, and I got it. So my last thought here is a tip. When we're finding the centroid, it's helpful to do a reality check afterwards by comparing it to the picture. Because we said earlier that we expect it to be on the z-axis, and I expect it to be kind of closer to the top than it is to the bottom. And that makes sense if the z-coordinate is 3/4, like I'm getting. So that does make sense. Okay, and there we have it.